Okay, I guess I can start it. Hi everyone, this is Emre. Today I'm going to present a paper which name is Variable Spin Charge Conversion across Metal Insulator Transition for Biospin Journal Club. This paper is published in Nature Communications in the year of 2020. As we can see here, for this paper, there are many authors and contributors. Before mentioning to this paper, I want to give simple introduction about the spin charge conversion and its efficiency. The functionality of spintronic systems is determined by the three basic process. These are spin injection, spin manipulation, and spin detection. For this reason, people who want to produce devices with low energy cost by increasing the efficiency of spintronic devices have been trying to provide pure spin currents without any transfer of charge current, since spin injection performed by Johnson and Silsby in 1987. At this point, the importance of charge to spin conversion efficiency in spintronic applications was discovered. Under normal conditions, this conversion efficiency is due to the structure of the material itself and does not easily change without chemical or structural changes. If we move on the article, this article mainly deals with the charge spin conversion efficiency was investigated with the help of the metal insulator transition in vanadium dioxide. Before going into the details of the paper, I would like to touch on the underlying effects and material structure of these studies. First, I will start with the inverse spinel effect. As we can see in the figure, here E is the electric field, GC is the charge current, and GS is the spin current. In the inverse spinel effect, converts an incident spin current into a transverse electric field, basically. Secondly, I will continue with the ferromagnetic resonance, which called FMR, driven spin pumping. This process is one of the most efficient and powerful methods for pure spin current generation. For years, people have used this technique for charge spin conversion characterization of paramagnetic, ferromagnetic, antiferromagnetic metals, also semiconductors and superconductors. I will touch on these effects a little more in the schematic representation of the sample used in this article. Now, let's look at the structure of vanadium oxide, which is the main material of this article. In both figures, vanadium atoms are shown in purple and oxygen atoms in pink. Figure A shows the monoclinic structure, which is the low temperature phase of vanadium oxide, while figure B shows the tetragonal or other name is rutile structure, which is the high temperature phase. In addition to the fact that vanadium dioxide has a wide resistivity range, it exhibits a monoclinic insulating phase at temperatures below 340 Kelvin and transitions to a rutile metallic phase at temperatures greater than the 340 Kelvin, providing a very suitable environment for studying fundamental spin physics under phase transition. Okay, let's now take a look at the structural properties of vanadium dioxide, YIG bilayer. Firstly, YIG films were ground on the gadolinium gallium garnet, which called GGG substrates, to examine the charge to spin conversion properties of vanadium dioxide. And then vanadium dioxide thin films were deposited on this stack by RF radio frequency sputter method. Actually, the sample preparation process is explained in detail in the method section. If you want to analyze deeper, you can check out the article, because at this point, I would like to talk about sample characterization and experimental results. Figure 1a shows the X-ray diffraction of the sample from which clear monoclinic phase peaks can be identified. According to this diffraction graph, the vanadium dioxide bilayer has a maximum intensity at the scattering angle of about 32 degrees for the 011 plane and at a scattering angle of about approximately 43 degrees for the -211 plane. It should also be noted that these angles are true thetas. On the other hand, in figure 1b, the surface morphology of sample was observed using atomic force microscopy, which called AFM. Okay. Other types of things studied for material characterization are their electrical and magnetic properties. In figure 1c, we see the resistivity versus temperature graph. In this sample, 4-point resistivity measurements were made on vanadium dioxide films for metal insulator transition detection. These resistivities were created with the help of the current potential difference graph created by the thermocouples mounted on the sample surface of the measurements made at certain temperatures. So at this point, the resistivity is measured as a function of temperature. Based on these measurements, the intervals with dramatic decreases are seen in the figure. In addition, hysteresis loop formation can be clearly observed in cases of increasing and decreasing temperature, as we can see blue and red color. On the other hand, in figure 1d, we see the variation of magnetism with temperature. Magnetic measurements on YIG films were made using the squid magnetometer. Superconducting quantum interference device, I guess, which called SQUID, is a very sensitive magnetometer used to measure extremely low magnetic fields. The measurements here were repeated before and after the vanadium dioxide was deposited, but it was observed that the values didn't change. In addition, the saturation magnetization of YIG film denoted MS after vanadium dioxide deposition is approximately 140 electromagnetic unit over centimeter cube at 300 Kelvin. As can be easily seen in the figure, MS change less than 30% over the temperature range in the experiment. Right then, this leads directly to my next point, which is measurement setup. The schematic of the setup used for the spin pumping measurement is illustrated in figure 2a. As can be seen in the figure, the samples are placed in a coplanar waveguide, which is CPW, with the vanadium dioxide YIG bilayer film facing down. The spin current from the magnetic resonance of the YIG layer is injected with vanadium dioxide along the y-axis, which called GS, and there it is converted into transverse spin pumping voltage, which called VSP. At this point, ferromagnetic resonance was triggered by external magnetic field under the control of sample temperature, thermocouple, and temperature controller. Thus, with the help of a DC voltmeter, the inverse spinel effect voltage could be measured across the vanadium dioxide layer. In figure 2b, spin pumping spectra are shown for the vanadium dioxide and YIG bilayer at 19 and 270 degree angles for 20 centigrade in plane areas. Under these conditions, thermal additives could be ignored. In addition, since YIG is an insulating ferromagnet, there is no contribution from anisotropic magnet resistance, which is AMR, and anomalous Hall effect. So based on all this, it has been observed that the main effect here is the inverse spinel effect. And when the injected sign direction is reversed, there is a sign change due to the inversion of HX. Okay. In addition to the experimental setup and some measurements, we should look at the observation of variable spin charge conversion in vanadium dioxide. As we can see in the figure 2C, the measurements were made at different temperatures. For this reason, a ceramic heater controlled by a PID controller is attached to the sample. The main purpose here is to investigate the variation of the spin pumping signal. When look at the figure, transverse spin pumping voltage and external magnetic field curves are obtained for a vanadium dioxide is 6 to 8 nanometer and YIG is 3 micrometer sample at a microwave frequency of 8 gigahertz between 20 degrees and 100 degrees. Here, as the temperature decreases, we see a decrease in the magnetic field value, a shift to the left, and an increase in the VSP peaks while observing. We can look at the 2D graph to see this change more clearly. Here the VSP values are represented by a star, and as it can be easily seen, higher peaks are reached at low temperatures. There is a decrease about 80% across the across the temperature range. Based on the resistance change on the site, we can easily say that this decrease coincides with the transition of vanadium dioxide from the insulator to metallic phase. So now I want to look at the same sample for different thickness, and we can compare the experimental results and Kittel's formula calculation. In figure 3A, we see a behavior similar to the graph I just showed. However, the thickness of the YIG layer in the sample we are considering here is 100 nanometer. In other words, a similar behavior was observed in the spin pumping signal samples with thinner YIG films. From this point of view, it can be said that the observed phenomena is not dependent on YIG film properties. In addition to the change in the transverse spin pumping voltage magnitude, a shift in the peak point of the spin pumping signal is also observed. This can be explained by the decreasing saturation magnetization, which is called MS, and at higher temperatures. Also, here is the Kittel's formula. In this formula, there is a resonance frequency, which is omega, gyromagnetic ratio, which is gamma, saturation magnetization, as I said, which is called MS, and resonance field, HRS. According to this formula, for a fixed driving frequency, a decreasing MS necessitates in a higher external field to satisfy the resonance condition. The resonance field HRS is plotted with the help of the temperature dependence of the magnetization curve. On the other hand, as can be seen in the figure 2A, the experimental results and the results calculated with the help of the Kittel formula are consistent with each other. Okay, this brings us to the next point. Comparison of platinum YIG bilayer and vanadium dioxide YIG bilayer. As can be seen from figure 2F, the size of the VSP changed negligibly with increasing temperature in the platinum YIG sample. In general, the spin pumping voltage depends on several fundamental material parameters, such as resistivity, spin mixing conductance, spinel angle, and etc. For example, an increase in the spin mixing conductance will enhance the injected spin current and raise the detecting signal, uh, while a decrease of the resistivity across the transition can directly lower down the spin pumping voltage. If we recall the graph of the vanadium dioxide YIG bilayer in figure 2C, another conclusion we can draw from this is that under the same conditions, VSV shows opposite signs for the platinum and vanadium dioxide samples. From this point of view, it can be emphasized that vanadium dioxide has the same negative spin Hall angle as pure metallic vanadium. Also, the large change in spin pumping voltage with temperature change provides the first evidence of phase-dependent spin charge transformations in this material. Now let's talk about the Gilbert damping coefficient. Here we can see the spin mixing conductance and ferromagnetic resonance line with expressions. Spin mixing conductance can be defined as the flow rate of the spins leading to the formation of the inverse spin-Hall effect voltage and is determined by the differences between the interfaces. In this expression, G is the lambda factor, nu B is the Bohr magneton, and alpha is the Gilbert damping coefficient for vanadium dioxide YIG bilayer and bare YIG. And finally, TF gives the thickness. When we look at the ferromagnetic resonance line with expression, which can be used for different resonances, we see that if is directly related to the damping coefficient. In short, it is very important to extract the Gilbert damping coefficient for the correct determination of these values. Let's take a quick look at the figure 3b. Only the observed damping coefficients for the YIG sample and the vanadium dioxide YIG sample are indicated. It was observed that the bare YIG remained largely unchanged over the damping coefficient temperature range, whereas the vanadium dioxide YIG sample showed a spike when the temperature rose about 60 degrees Celsius. From this, it can be said that there is an increase in spin pumping during the metal insulator transition, indicating a large increase in spin to charge conversion efficiency. As a final point, I would like to say that this article experimentally demonstrated phase-dependent spin charge conversions in vanadium dioxide with the help of ferromagnetic resonance-driven spin pumping and inverse spin-Hall effect. During this metal insulator transition, a dramatic decrease in spin pump signal and a sudden increase in spin charge conversion efficiency are observed. From this point of view, the use of charge to spin conversion in areas such as 2D materials, Rashba interfaces, topological insulators, superconductors, etc., opens up opportunities for the engineering of spintronic materials with various functions. So to improve the conversion efficiency for vanadium dioxide and to see the effects more clearly, it may be helpful to use films of higher quality with the more distinct phase transition and greater metallic phase conductivity. And these are my additional sources. In addition, if you are interested in this subject in general, you can find additional measurements such as some control experiments, spin charge conversions for different thicknesses of vanadium dioxide films, also spin pumping results for different driving frequencies, etc. In the supplementary part of the article, I couldn't add it to the slide because I didn't want to get too dispersed in this article. Finally, thank you for your time and your attention.